Okay, great. Okay, so far, what did we do? We had this thing, the shuffle conjecture that we've been trying to prove. And essentially what it was trying to, or what it was saying is that if you take nabla of En, this is supposed to be, t to the area of pi, q to the div of pi, times some sort of symmetric function, right? Chi w. And essentially this was really this should not be, they should not be both pi's, but when we had this expression, really the first thing that they did is they changed area and div for bounds and inv, right? So step one in this decomposition, let's say, step one in the proof was to change area and div for the statistics of bounds and inv, right? So that was its own combinatorial process. Okay, so then now that we had this nabla En expressed in terms of bounds and inv, they rewrote this expression so that instead of having a sum over monomials, we had a sum over t to the area, but instead we had this chi pi of 0 showing up, right? So the q was already baked into the definition of this chi pi 0. And then recall that this chi pi 0 was equivalent to the function that we saw previously. I think Aram talked about it, this f sigma or f pi, I think is what it was indexed in Hagelin's book. So we've seen this function before. It's a symmetric function. And then this should probably be step 2. The next step in the construction, or the next part of the proof, let's say, was to basically define a whole family, a whole slew of these characteristic functions for Dick paths, right? Some were weighted, some were not, right? And they basically called them, the two outstanding ones that we really cared about were these chi pi 1s and chi pi 0. Right? And there were 0 and 1 were just the weights. You could define them arbitrarily for any weight that indexed your Dick path. And fundamentally, the main takeaway from this construction was the fact that you could first of all, you could define chi of pi 0 from chi of pi 1, right? There was this this recursive formulation where you would just change the weight one piece at a time. And then the second important part of this was the fact that chi pi 0 satisfied this property, or sorry, that chi pi 1 and chi pi 0 could be constructed from these raising and lowering operators, right? So I guess step 4 was this to define these operators, right? This d plus, d minus, yi, and ti on this family of vector spaces that we called vk, where here vk was basically the ring of symmetric functions, right? So let's try qt with variables x1, etc., symmetrized, tensored with just a polynomial ring in k additional variables, right? So this is just basically symmetric functions with some extra variables. That's what vk was. And we saw that these operators, d plus, d minus, acted as raising and lowering operators. So they were defined with some sort of plethism, right? Where d plus basically took you from vk to vk plus 1, and then the d minus would take you from vk to vk minus 1, right? This yi was just acting by basically multiplication by the variable yi. The ti's were acting by de Moivre-Lustig operators, right? So they were Hecke algebra generators, essentially. And what we saw, which is related to this step 3, is that basically you could construct these totally combinatorially defined functions out of these d pluses and d minuses. Namely, you could define this function to basically, if this was indexed by pi, to be a series of, let's say, north steps, and then east steps, n1, and so on, northeast, whatever, to some coefficients. Then you could just substitute the north steps by d minuses and the east steps by d pluses. And you could obtain the exact same function, this symmetric function, by just acting according to this dict path by these d pluses and d minuses on one, right? So then you would basically get that this this function was really kind of, let's call it d pi, because just as a shorthand, right? D pi of 1. And likewise, this chi pi 0 could be obtained from these raising and lowering operators by instead, at every corner in the dict path, right? Anytime you saw something like this, you would substitute that by the commutator of d plus and d minus. So this was also obtained in the same way. So obtained similarly. Right. And so that gave us basically a link, a way of constructing these functions by appealing to these operators. And the interesting part is that when you were constructing them, right, you didn't necessarily stay in the ring of symmetric functions, right? Because a lot of the times when you're doing maybe too many d pluses, you jumped into these higher spaces, right? These V1s or V2s or V3s. So you had Ys hanging out, but because eventually you came down again, you applied sufficiently many d minuses, you do return to the land of symmetric functions, but you took this detour. And it was really cool to see that, oh, well, basically adding a north step to pi was equivalent to us acting on that function that you had, that symmetric function, by a d minus, and adding an east step was the same as acting by a d plus. So there was a complete correspondence between the creation of these dict paths, or these dict path functions, and these operators, right? So that was the big main takeaway here. And then we also saw last time this operator, right? So the main content of last time, and I'm just gonna backtrack because I think it's easier to just see it written here. Where did it go? Was this operator n, right? So we basically at this point, we know how to generate the chi's, pi 1, pi 0, whatever, using our d pluses and d minuses. And the next thing that we wanted to know, was how to incorporate the t's, essentially, right? We know that this, the shuffle conjecture is essentially telling you, right, that this nabla en, so this which is what we were calling d alpha qt, because that's what they use in the book, or in the article. So this is supposed to be t to the area times chi of pi 0. So we know how to construct chi of pi 0 of d pluses and d minuses. The next step is incorporating the t's through some operator that is acting on these new vector spaces, right? And that is where this n alpha comes into play. So what we did is we defined recursively this operator. We called it n alpha, and it acted basically by sequences, right? For any composition. If you had an empty, you started with 1, and then you recursively built your composition, and you generated something, some sort of strand of d pluses and d minuses, right? And the main theorem that we proved last time was the fact that by doing this, by acting by these n alphas on these operators, d plus and d minuses, you got the corresponding sum that you wanted, right? Nabla of en, or at least the right-hand side of that equation, this combinatorial expression, using just the operators in these d pluses, d minuses, and you incorporated the t. Right? So this was the big theorem at the end of the last session. And just as a reminder of what this n is doing, right? We did an example where, right, if we had alpha be the composition 3, 1, then we just slowly went through and built it recursively, right? And we took a bunch of steps. We're like, okay, what's going to happen is we start with empty, we get 1, then 1 empty, we just follow the recursion, we get 1, then we do a 3, 1, and that 3, 1 is going to decompose recursively into smaller pieces, some smaller n's, which we then individually did, again, just applying the recursion. And what we found at the end was that this n31 essentially decomposed into a sequence of dict path functions. So I didn't do it here, but if you actually go through and work this out, this n31, so this and this decomposes into, basically like d plus or d minus, d plus, and so on. So 6 terms a sum of 4 terms, each of which has 6 products of D pluses or D minuses. So if you, it's basically just if you undo this the commutator, you get 2 terms out of that, and so on. And the point is that each of those 4 summons that show up in this expression, the 4 summons that show up here, are each indexing a different dict path with touch point 3, 1. So n3, 1, this recursion, is somehow combinatorially telling you exactly what all the dict paths that you get with touch point 3, 1 are, and it's indexing them precisely by these D pluses and D minuses. So that's what that recursion is doing. Fantastic. And that's where we left off. It was basically improving this fact. Good. So then what we want to do today is basically, oh, sorry. And then once we had that in hand, we proved some things that will be more useful today, which was basically the fact that you could encode all this information, all these operators, D pluses, D minuses, TIs, and whatever, into an algebra, which they called A. And they showed that this algebra A basically acted on your space V, and it was a representation. So you had a representation of this algebra A, subject to all these crazy relations, right? Which they're just relations. You can think about them, but basically they're just useful for the purpose of the proof. They're just useful in generating exactly what you need them to generate. So I don't want to spend too much time dwelling on what's going on there. Yeah. And so then once we had this representation of A, I think that's where we left off. Oh no, sorry. And then once we had that representation of A, we had the following theorem, which was not only was this vector space V, which is, just as a reminder, V here is supposed to be the direct sum of all these smaller vector spaces, Vk. So k bigger than or equal to 0. So not only do all our operators D plus, D minus, Yi, and Ti act on V in a cohesive manner in the way that they generate this algebra, they also actually not only act on it, but generate the vector space itself. What I mean by that is that if you had this projector PK, right, and you basically just treat it as like an idempotent that's projecting onto the kth vector space here, then you had an isomorphism of modules or an isomorphism of representations by just thinking of this algebra A, and thinking of all the operators after projecting them to P0, which is just symmetric functions, essentially restricting them to their action on symmetric functions, then you had an isomorphism of representations. And the reason that this was cool is because it gave us a perfect bijection between a basis for our vector space and a basis for this module, this AP0, this vector space AP0, where it sent essentially a very explicit sequence of D pluses, D minus, and Ys on this side to precisely the basis of V generated by Hall-Littlewood polynomials tensored with monomials in Y, right? And that's why this isomorphism is really cool, or one of the reasons why it was very cool. So just as a reminder, essentially what we had was that these monomials here, let's say, these monomials living in AP0, right, which are just basically, you act by D plus, then you have some monomial in Y, then you close it off with D minus, so you're ensured that you're living in symmetric functions, that this really does get mapped to precisely the Hall-Littlewood basis. So you get mapped to a product of these B operators, which is just generating some sort of modified Hall-Littlewood times a monomial in Ys. So it gives you exactly the basis that you would expect to get. This is where we left off last time. So now, what I want to talk about is nabla, finally. How do we introduce nabla into this equation? So any questions, now that I've spent, I think, like 20 minutes refreshing, sorry, but I figured it had been a while, so you probably didn't remember half of what we had talked about. So now let's talk about nabla. So what is the point here? We're not actually going to define nabla. We're going to define a modified version of nabla. And what I mean by that is we're going to define an operator that's going to be an involution on this vector spaces, V to V, right? And this involution is going to satisfy the property that when it's restricted to symmetric functions, right, when it's restricted to V0, it's going to act like nabla composed with the involution omega bar, where omega bar is just the involution that essentially swaps Hn and En here, and swaps Q and T with Q inverse and T inverse, right? So it's a standard involution on symmetric functions up to changing Q's and T's essentially, and composed with nabla. So it's almost nabla, good enough for us, as we'll see. So how do we go about defining such an involution? So in order to do that, we need to define this structure that is basically, we can think of it as an adjoint structure, or a conjugate structure really is what I should be saying, to A, this algebra A that we talked about before.
Sorry, so about this involution, can you remind us what does it do to Macdonald polynomials?
I haven't actually told you what it is yet.
Okay, but you will.
I will tell you what the involution is. Yes. I'm just saying what we're going to construct now is we're going to construct this involution. To construct it, we need some extra structure, and then we'll define it.
Okay, but like on symmetric functions, we know what it is, like on V0.
Yeah, we know exactly what it is on V0 because it's just...
Yeah, I guess I'm asking, so in V0, the base of Macdonald polynomials, nabla is diagonal on that.
So it should leave, yeah, I guess it should...
So it just the question, so what does omega bar does to H lambda? So you take H lambda, I think omega bar takes it to H lambda transpose or something like this. I never remember.
Probably because you're swapping Q and T, right? And I think I think if you take H tilde of Q inverse and T inverse, you get H tilde of lambda transpose. That seems right. But okay, I don't remember off the top of my head, yeah.
Okay, anyway.
Okay, and so then what we do is we define this new algebra, and we're going to say that it's generated by, essentially you can think of this as being the same as A. We're just relabeling the generators, right? And instead of having D plus, we're going to have a D plus star. Instead of having a TI, we're going to call it TI inverse. The D minus stays the same. And then the relations are basically the same relations that we have in A, all these relations that I flashed at the beginning, but we're going to basically swap the appropriate things, right? So we have the relations for A, and whenever we see a D minus, we leave it the same. Whenever we see a D plus, we swap it for a D plus star. Whenever we see a TI, we swap it for a TI inverse, and so on. And we swap every Q for a Q inverse, right? That's the game we're playing here. So it's really, as algebras, they're completely isomorphic. You're getting the exact same structure, you're just relabeling things. And analogously, just like in A, we had this element yi that was multiplication by yi. We're going to construct a new element in this algebra, A star, which we're going to call zi. And zi is defined just like yi was, but where instead of a D plus, we see D plus star. So it's really the same structure. Okay, great. And why do we want to do this? Well, because
Nicole, question?
Yes, please.
So here you have a zk, and then you have with zi equals. What's the difference between the k and the I? Like, is k, like, it looks like I'm confused about this. Sorry.
Yeah. Okay, so this is, we want to view this as living in VK, and this living in VK. So
so here I is strictly less than k in the second one? Yeah,
exactly. For I, it's less than or equal to k. And we'll see that this right now doesn't really make a lot of sense because I haven't told you that these, how is this living in a vector space VK when VK only has variables yi? So this is like, I want I to be less than or equal to k. So maybe let me say this. For I less than or equal to k, and I'll tell you why these are actually related to VK in a second, right? Because at prior right now, the ZIs have nothing to do with YIs, right? You can't. So we need to define an action, and I'll do that in a second.
Thank you.
Yeah, absolutely. And okay, and so then once we have this algebra, we want to define a new operator. The reason for that will become apparent in a second, but we need to find an operator gamma that's basically just going to move the yi's around. It's going to rotate them. It's going to send yi to yi plus 1 and yk plus 1 to yi times t. Why is this important? Because realize, you might remember that, or you might not, but I'm telling you that the algebra A in the generators, in the relations for the algebra A, and therefore in the relations for the algebra A star, there are no t's. all the relations only involve Q's. So how on earth are you getting T's out of these operators? So one way that you do it is precisely by this operator gamma, which will play a role in the actual action in the, in the module structure that we're getting. So here, that's where that T shows up, right? And so then with that in hand, we get the following. We get that V is actually a representation of A star, right? So that means that this algebra A star is going to act on our V's, all VKs. And the only thing that we need to define in order for this action to make sense is what D plus star is, right? And so here, D plus star is going to act by basically the same plethism that defined the D plus without the star, but instead of conjugating it by a bunch of TIs, which was the original action, we're going to conjugate it by this gamma. So this D plus star is going to be spitting out T's. And notice that once we have what the D plus star action is, if we go back to the definition of the Z's, right? Well, the action of Z, since Z is defined in terms of D minus and D plus star, if we know what D plus star and D minus are doing, then we know what the Z's are doing. So that we get for free. So then it makes sense to think about these as operators on our vector spaces VK. Do you guys have any questions? Okay. So at this point, we've just defined some representations, great. And one thing that you might ask is, well, we have these two representations, A and A star, on the same vector space. Do they interact in any way? The answer is yes. And when you actually go through and check how these representations are interacting with each other, you see that they're going to satisfy these four relations. And that's just, there's the way you do this is you just sit down and check it. There's nothing, it's a straightforward computations. There's nothing particularly exciting. Okay, good. Now,
can I say one thing? So this
yes,
equation in the left bottom corner is the only equation which involves T, as far as I understand. No, the left of it.
This, yes.
This one, yeah.
It is the only, that's a very good, yeah, that's a really good point, that this equation, let me actually mark it in red. This is the only equation in all of the relations that we've seen so far of A and A star that have any T's in them. Exactly. Yeah. Good. And that should somehow make sense, because the D plus is somehow spitting out T's, but the D plus star is somehow spitting out T's. The D plus is not. So you need some T's to counterbalance this. Off the top of my head, I would imagine this would be a T inverse, so I'm not sure why it's not a T inverse, but maybe this somehow you get a T inverse out of it. I'm not sure. Anyway, so then somehow these equations work out. And then with that in hand, we want to define, as we'll see later, an analog for this N alpha operator that we saw before. This N alpha, remember, was the operator. So just as a reminder, we had this operator N alpha, and morally what we had is that if we applied N alpha to this, we got D alpha. There are some coefficients here that I'm missing because I don't remember them off the top of my head, but essentially you took an N alpha, right, this recursively defined operator that gave you the T's, right? This was the way that it gave us T's from the chi pi zeros, essentially, right? And what we want is some similar formulation for this, as we'll see in terms of the Y's. So this analogy will make sense towards the end of the talk. So just keep this in mind. So we have this proposition where we're going to define essentially this new operator called Y alpha, very similarly to how N alpha was defined in terms of recursions. So namely, we have a weak composition. We're going to set Y alpha to basically just be the product of these variables yi with some powers, okay? Nothing exciting there. But the point is that these monomials Y alphas satisfy the following recursions. And these recursions, right, if you have it written somewhere, or if you want to go back and look at the notes, you can sit down and actually compare, and you'll see that these recursions are basically the same ones, or very, very similar to the ones that N alpha satisfied. And that'll play a big role. So the proof is just a computation. Again, you just sit down and check it. It's actually very similar to the proof for N alpha. So I'm not going to tell you, I'm not going to go into the details of that. And now we're going to define this algebra AQT. So this is kind of the big algebra of the paper. And essentially what this algebra AQT is just a way of encoding, of grouping the algebra A and the algebra A star into one coherent unit, right? One structure. And it's literally, you take A star, you dump them in the same bag, you put them together, same generator, same relations, but then you quotient by additional relations. You impose the additional, this is not a relation here, by the way. You impose the additional conditions that these three relations have to hold. So let me just quickly go back, right? And one of the things that we saw in the previous theorem was that if we take A and A star independently as independent actions, right, they satisfy these four relations. So all we're saying is, let's just group these two actions into one action, define this new algebra. We're going to call it AQT. And the QT is going to come from the fact that it has variables Q and T showing up in the relations, right? We're going to call it AQT, and we're going to force it to satisfy these three relations, just encoding it into some structure. We're not going to enforce this relation, and that will play a key role in a second, right? Just these three. So then once we do that, then it's actually very obvious that this algebra or this vector space V is a representation of AQT. Why? Because we had an action of A, we had an action of A star, they satisfied these three relations. So it follows that it's a representation is very, very straightforward. Again, the interesting part here comes from the following statement, which is the fact that this map, that you can play the same game where you take this algebra AQT, you can think about it as just acting on symmetric functions. You get some sort of span of elements. That's going to be some sort of vector space. And on that vector space, you can think of the algebra acting on it, on itself. So we get some sort of module for AQT, some sort of representation. And as a representation, that space has a map into V. This map is not an isomorphism. It's just a map. But it's a map of representations, right? So it commutes with the action of AQT. And the statement of the theorem is that this map has kernel exactly given by that extra relation that we didn't bake into the definition of AQT, right? And what that tells us, and this is just basically, an isomorphism theorem from algebra 1, is the fact that this map or this vector space V is equal to the image mod the kernel, right? Or essentially that it's this space modulo this ideal. And we'll see that this isomorphism is key in proving some stuff, actually in justifying why the involution exists that we want, this n involution that's going to give us nabla. So do I want to talk about the proof?
What's P0?
P0 here is projection onto V0, like the P0 idempotent that projects onto the copy of V0. Yeah, actually, let me say some words about the proof, because I think it's a little bit interesting. So this I don't have written down, but it's okay. I'll just write it. Because we're basically, once we have this, the involution, the proof is really very trivial. So let me cut this. Ah, no, come back. Cut. Let me move up here. So let's discuss the proof a little bit of this. So how do you prove this? Or what's the story behind the proof? So essentially, what you want to remember is this isomorphism that we talked about at the beginning, right? The fact that AP0 was isomorphic to V. I recalled it earlier today at the beginning. And essentially, right, remember that what this was doing is it was sending this basis here to the product of essentially modified Hall-Littlewood's with monomials in Y, right? Some monomial in Y. Essentially, this is what this basis was doing. And it was sending the subspace here that was generated by essentially projecting then onto the kth copy or composing with the kth idempotent this was getting mapped isomorphically to the piece VK, right? So this was the content of that theorem. So now with this in hand, so recall, what that means is that we have, so AQT is going to act on V, and it's going to satisfy the right relations, obviously. But in particular, this map AQT P0 to V, it restricts to this map star to star. So it already knows about this map, right? So you have this projection that you get by, well, kind of for free. It's not a very complicated map to just see that it exists. But the point is that it restricts to this isomorphism. The reason that we care about this is because it allows us to basically see that if we have, it not only restricts to this map, it's surjective. It's a surjective map. And the reason that we care about this is because it allows us to see that if we look at the map AP0 to V, this isomorphism actually factors through the following quotient. So we have AQT P0, and if we quotient it by this additional relation, D plus star, D plus of M minus D plus M plus 1, which is essentially just the ideal generated by that extra relation, that this isomorphism factors through this quotient, right? Why is that? Because if we just look at the relations that held between A and A star, this was the only relation that was missing. And so the fact that this is surjective tells us that this is surjective. So this being surjective tells us that this is surjective. And what we want to argue, basically the goal of the proof, is to prove that AP0 is in fact isomorphic to this quotient, to this AQT P0 quotiented by this ideal, which we're going to call I. We call this I. So the fact that it's we don't want it to, let me say this, we don't want this to be isomorphic, we want this to be injective. We want this to be an injective mapping. Right, and the way they do this is not that hard, it's just computational. So the way they do this is they basically say that this is graded and this is graded, and they prove it on each graded component. So what ends up happening is basically you impose a grading by saying, well, we're going to let D plus, D minus, and D plus star have degree 1, right? Because remember that every element in both of these spaces are generated by these D plus, D minus, YI, etc. operators. We're going to impose the condition that that YI has degree 2 and that TIs have degree 0. And then you can check that these are compatible with the relations, compatible with the AQT relations, right? And then once you have this compatibility, what you end up showing is basically that if you let AP0, you can think of this as being graded by, let's say, some degree M, and then AQT P0 quotiented by this ideal, you let this also be graded by some other vector spaces where you have homogeneous degree M up to, indexed by these degrees, then what you show is basically that Vm is isomorphic to W of Vm for all M. And you do this inductively. So the base cases are easy. And then for the inductive step, you essentially assume that, or what you show. So let me maybe write a little bit more. So here the proof is by induction. And what you show is that if F is in Vm, which we're going to assume by the inductive hypothesis that this is equal to Wm, then D plus star of F lives in Vm plus 1, right? The reason that this proves it is because this D plus is supposed to live in AQT. So it a priori doesn't really live here. It lives here. But since we're assuming that Vm M and V and WM are the same, then D plus star does act on it. And what you want to show is that when you act on this side, you still basically live on this side. And then that really, the proof itself is not very exciting. At that point, you basically just write F in terms of the, so I'm going to call it the Y alpha dot Hall Littlewood basis. And what I mean by this is that expression of yi's times d pluses times d minuses, et cetera, that mapped to this basis under the isomorphism, right? So you can write this generically in terms of this basis because it's a basis. And then you just check d plus on this expression, and it devolves into a case-by-case proof. It's not very exciting. Expression, case by case.
I have a question. I wondered that.
Yeah.
So you had said isomorphism, and you said, wait, injection, but then here isomorphism. So wouldn't that mean isomorphism?
Yes, so you're proving an injection. You're proving that it injects, but it implies that it's an isomorphism.
Okay.
Yes. Yeah, and so at the end, you get that it is an injection, and thus, it's actually an iso. Which is great, because then if we go back to our statement here, what this is telling us is that precisely this, that this vector space V really is generated by this space, because we already knew, right? That was the whole point of this theorem. We already knew that AP0 was isomorphic to V. And what we showed is that this quotient is isomorphic to AP0, which is isomorphic to V, therefore we get this. That's the content of the statement, right? Now, why do we care about this isomorphism? Because that's where the involution comes into play, right? Because essentially what this is telling us is that we have an involution on this algebra AQT. What is that involution? Well, by definition of AQT, what did we do? We took A and we took A star, which are basically the same, except that you have, D plus gets sent to D plus star, YI gets sent to ZI, and so on. And that's exactly the involution. It's the fact that here, this is, the map that's sending D plus to D plus star and vice versa. So it's swapping these two. D minus is fixed to itself. YI is involuted by ZI, and then of course TI is mapped to TI inverse. So the involution is doing this. It's very obvious that it exists. And in particular, it's the one that's sending A to A star. So that one makes sense. But most importantly is that it actually preserves this kernel, right? So somehow, and I tried checking this by hand and I couldn't actually do it, but I'm assuming that it's true because they claim it's true. That if you look at this kernel, which was, just as a reminder, right here, we have kernel of this psi was that extra relation, right? This. And so the claim is basically that this kernel, or the ideal generated by this element, is invariant under that involution. And therefore, that involution actually preserves that subspace, or that ideal. But if it does, and again, I tried checking this. Sorry?
Sorry. So I'm forgetting, there's so many different normalizations with quadratic relations and so on with the T's. So does Q go to Q, or is it Q goes to Q inverse?
Q goes to Q inverse and T goes to T inverse.
Right.
So the fact that this involution preserves this kernel was not obvious to me. So if anybody knows how to do it quickly, that's great. They didn't give any details on it. They're like, yeah, it just does. And like I said, I tried checking it, and I'm assuming it's some sort of clever application of the relations, but maybe there's a smarter way of seeing that. If it does, and let's just assume it does, then what that tells us is that this involution doesn't just, doesn't just involve AQT, it actually involves the vector space. Because if it's an involution of AQT, it's certainly an involution on AQT P0. Since it preserves the kernel, it actually also preserves this quotient. So it's an involution on this quotient. And what that means is that it's actually an involution on V, because by the previous theorem, these two things were isomorphic, right? And that's where this N involution comes into play. This is where this Nabla operator is going to just kind of be popped out of all this weird, representation theory that's happening here. And this is the content of the theorem, is basically the fact that there does exist a unique antilinear degree preserving automorphism. We're going to call it N, that sends 1 to 1, and that it basically does exactly what we said in the previous statement, that it mixes and intertwines the A and the A star action. So it swaps between the two operators for N and N star, for A and A star. That's this. It's an involution, so it squares to the identity, because of course, if you first go to A, then by the involution, A is going to get sent to A star and so on. So they undo each other. And step 3, very important condition, is the fact that if you take this involution and you act on these Y alphas, these monomials that we had defined as, right, this was supposed to be, so this was like Y n alpha n minus 1, like y1 alpha 1 minus 1. And the point of that proposition was that this y alpha actually satisfied a bunch of recursions. Well, it turns out that if you act on this y alpha by n, you get modulo a constant of q, precisely this n alpha, this other operator that we saw previously that also satisfied very similar recursions, where this was basically eating these chi pi zeros, right? So what this is telling us is that this involution n is exchanging the y alphas for this operator n. And recall, right, this is, again, I'm going to say it 100 times over, that essentially it was like d minus to some power of n alpha was really giving us this d alpha qt, which was the goal of this whole expression, right? Key to proving the shuffle conjecture was that this is true. And then lastly, and this is kind of what we'll see, is that actually when you restrict this weird involution to V0, to just the ring of symmetric functions, you really are just getting nabla. So how do you prove this? So the first two, the fact that it exists and that it intertwines this in the right way and that it is an involution, that's pretty straightforward from the last theorem. Step 3, which is the fact that it intertwines y alpha with this n alpha, is basically just a consequence of the recursions, and the fact that you compare the recursions, you're getting two different objects, but the recursions are basically the same. So if you have two objects that are defined by the same recursions, they have to be the same, up to, conjugation by n. So 3 follows directly. And then 4, to see that it actually restricts correctly on the ring of symmetric functions, we need to define a couple of things. So the first thing is we're going to define these operators d1 and d1 star. On the ring of symmetric functions, there's some sort of plothistically defined things. And essentially what you end up doing is showing that this d minus and d plus can be used to generate this d1, that e1 can also be generated by this d plus and d minus, and that d1 and d1 star are related by an involution. And then you can also check that this d1 and d1 star, because of how they're defined, behave a certain way with respect to this n involution. So you basically sit down and you check that these things satisfy these properties. It's a straightforward check. And then you say, all right, let me set nabla prime to be this, the restriction of n composed with omega on V0. Since omega is an involution, it can move to either side. And what we're going to prove with this is that this nabla prime satisfies the same defining relations as nabla does. Therefore, they have to be the same. And that's why I'm involving all these weird relations. And essentially, you just go through and check it. And you're like, all right, well, under this definition, the nabla prime satisfies this condition, with respect to this weird operator d1, satisfies this condition. And then they just appeal to previous work of Garcia, Heyman, and Tesler that tells you that this operator nabla is actually defined and determined by these 3 relations. So if you have another operator that satisfies the exact same relations, it has to be nabla, and therefore it's true. So it's kind of clever that they could get these operators, the defining operators from basically all of the information in AQT. So somehow this algebra AQT really knows everything, which is pretty great. Good. So then we have finally, the proof of the shuffle conjecture. How do you take all these pieces and put them together? So this one I didn't write down because, you know, I wanted to write it out step by step for you guys. Any questions before we move to the final point, the pinnacle of this entire million, you know, week endeavor here? All right, let's just end it. So what do we do? So theorem, and this is really the content of the shuffle conjecture, which is for all compositions of length alpha, nabla of C alpha, right? That's what this is saying. This is just nabla of C alpha acting on 1 is really equal to this D alpha QT, right? Because this is essentially the content of the compositional shuffle conjecture. Remember that this side is supposed to be, you know, T to the area, Q to the div of chi W by definition, or bounds and inv if you like that. So why is this true? Proof. So we're going to start by massaging the D alpha side. So this is supposed to equal D minus K, there you go, that was the coefficient I was missing, of N alpha. That was the theorem we proved last time, right? Now, this is going to equal D minus of K of this curly N, this involution, applied to Q to the alpha minus K of Y alpha. Why? So let's, right, how did I get from here to here? Well, I just used the fact, this is literally the theorem we just saw, that if you apply this involution to Y alpha, we get Q to the sum of alpha I minus 1, right, times N alpha. So all I'm doing is I'm moving this Q to the other side. And then we get this. Good. So nothing too exciting there. Now we're going to do another step, and we're going to basically swap the N and the D alpha. So this is N of Q to the alpha minus K times D minus K Y alpha. Why? Because remember that N commutes with the D alpha, that this curly N, this involution of D minus.
Would your exponents on the Q actually be the negative of what you have?
No. Yeah, I thought that as well. And it's, so here's the thing. This one, when you move it to this side, you get a negative sign, right? But then if you conjugate it with the N, because N swaps Q and Q inverse, it gets negated twice.
And you brought it inside the N.
Because I brought it inside the N. I had the exact same thing. I'm like, it's a typo. They made a mistake. And then I was like, oh, wait, I'm being dumb. So yes.
Me too.
No, it's okay. I got the exact same thing. Okay, and so then here, all you're saying is that D minus commutes with the N. All is good. So now next step. Then at this point, we want to apply this condition that I mentioned a couple of times, and hopefully you guys remember, which is the fact that this, let me just write what I want to say, that this Y alpha acted upon by D minus, what you're going to get is this operator of Hagelin-Morse-Zabrocki, this B alpha that's a generator for Hall-Littlewood's, right? So this was a relation, this was using the fact that if you do D minus of YKI of F, that this is just minus BI plus 1 of F, right? So the minus comes out to a minus 1 to the K, and basically, yeah, remember that all of these are secretly acting on 1, right? So this is all of 1. There's a of 1 here hanging out. Good. So here we're just using that identity that you can prove directly by definition. There's nothing very special about that one. So it's almost trivial. And then we're done. Why? Because this N, right, is really just N of omega bar of C alpha of 1. So what was the C alpha? Remember that when I told you what this B alpha and the C alpha was, I told you that they were related, right? So these are related by the fact that Cm can be obtained by taking 1 over Q to the m minus 1 and then conjugating this Bm by this involution. So what that tells us here is that, well, I just conjugate by the involution and I get precisely this. Okay, Cool. And that even the Q goes away, which is pretty awesome. And then at this point, we're done. Why? Because n omega restricted to symmetric functions and C alpha of 1 is a symmetric function by work of Hagelin-Zabrocki-Morse, then this is nothing more than nabla of C alpha of 1. And that finishes the proof. So proof is incredibly beautifully short, and it just follows from a bunch of identities that were not so trivial and not so short to prove. And that's it. Questions, comments, concerns? You guys believe it? Yay, we're done. It only took a month. Thank you for sticking with it, guys, and not running away. Okay, questions?
I have a comment.
Yes, or comments.
Maybe people ask questions first and then I'll say a comment. Yeah, I'll wait.
I think you just comment, Eugene.
Okay, I just commented and people ask questions later. So if you scroll up to this operator D1 and D1 star.
Yeah.
So there is a big family of operators on symmetric functions.
The DK.
Basic DK, yes, but also like the key thing is that there is a SL2Z action, or like quarter of SL2Z, whatever, like some part of SL2Z action on this algebra AQT.
Mm-hmm.
So one operator in SL2Z just swaps AQ and AQ inverse, and this is this involution.
Mm-hmm.
But there are more, and so later Anton essentially proved that there is a SL2Z action.
Mm-hmm.
And it gives you a whole family of operators on symmetric functions, which are parameterized by points in Z2.
Mm-hmm.
And so some of them are just E1, some of them are this D1 and D1 star, and there are more, and they're related to this beautiful structure called elliptic Hall algebra and lots of other things. And that's, yeah. But in principle, all of them, they sit inside this algebra. You can just think of it as like acting by this involution and another generator of SL2Z and just applying these things and getting more and more and more interesting operators on symmetric functions. But somehow, if you try to write these operators without knowing that they come from AQT, it's really messy and it's hard. And somehow you can write them in Magdalene basis, but it's really tricky to write them without knowing AQT algebra. So I think that's like one advantage, that you can cook up lots of interesting operators on just the base symmetric functions without going there. And they're nicely intertwined by nabla. Huh?
Is it really Z2 or is it kind of more of an upper half plane? Because of
it's a quarter plane, I think. Like if you want
N2.
N2, yeah, I think so. I mean, yeah.
So you can embed the entire elliptic Hall algebra or just some part of it into AQT?
I think the quarter of it.
Yeah,
like where all indices are positive, not negative. I mean, it's a question if Z's and Y's are invertible or not. So Y's are certainly not invertible. Z's are invertible in this representation. So you can just like, it's a question how you define this AQT in some sense, right? You cannot define it so that Y's are invertible because that would mess up things. But you can define them that just half of them are invertible, and then it will be half plane, I guess. But if none of them is invertible, you have just a quarter. I think I confused everyone, but that's fine.
I mean, but I'm probably not the person that needs to be convinced here.
No, but I mean, sorry, maybe I'm being dumb, but how can C is being invertible and Y is not if there's this involution that preserves V0 in some way and interchanges Y's and C's?
I mean, it will be it will send polynomials in Y's to polynomials in Z's, but no the inverse. So it will, and then it won't be defined on things with the inverse. So it will be kind of partially defined.
Okay.
I don't know. But like, I mean, concretely, so you like one type of operators on symmetric function that you can get is you go by D1 to V1. And then there you have just two operators, Y1 and Z1. You don't have T's at all, but but Y1 and Z1, they don't commute. So you can write any word in Y1 and Z1 and maybe Z1 inverse, and then go down to V0 by D minus. And so you can get like all these operators from elliptic hole, you can actually write them as d plus, then some word in y1 and z1, and then d minus. Or maybe d plus.
You wanna? Can I ask you to maybe say like a word or two on why the elliptical algebra matters, just for everybody here who might not know, or not.
I mean, I don't know. It's cool. I mean, it's a long discussion. I don't know.
That's fair. That's fair.
It's related to nice geometry. It's related to nice algebra. I mean, I don't know.
I mean, classic Hall algebras have to do with counting extensions.
Yeah. This is still how many extensions, but you just look at like line bounds and elliptic curve over fine field. It's
Anyway,
like whatever.
let me just say before we get too carried away and people can actually ask questions, I think we're getting off track here. All of these comments have to do with the fact that there's a general version of the shuffle conjecture, a more general version, that instead of just counting paths on n by n grids, you count them on n by m grids, right? And so there's a whole generalization of the shuffle conjecture, which is actually due to Eugene and Andre Nagutz, where you, well, yeah, basically it's the analogous thing where you have an operator and you're acting on one and you end up with a sum over dict path functions. It's a very, very similar statement, but you're not summing over n by n, you're summing over n by m. This was also proven to be true, and it by Anton Mallet, who also, wrote, was half of the authors in the proof of the original shuffle conjecture. And the way he did it is exactly by this thing that Eugene was just talking about, by basically kind of defining this SL2C action and realizing it. And so in that story, these operators play a much bigger role. That's kind of where this was going. So for those of you who didn't understand what just happened, let me apologize and kind of explain a little bit. But that's a different story and it's a different paper. Also hard, also long, also probably would take a month. So let's not go there. Yeah, does anyone have any questions though, or any examples they would like to see? Because I feel like this is all very heavy and not a lot of examples were given. Or anything they'd specifically like to see computed.
I would love to see something explicitly computed. I'm trying to come up with what would be a good example.
Mm-hmm. That's why I didn't pre-plan anything, because I was like, I don't know what is confusing here. We've seen chi of pi 0. We've seen how these things, how you get symmetric functions out of this by d plus and d minus. We saw the decomposition d31 or n31 into dict path, those four dict path symmetric functions last time. I am not sure what a good example is.
I don't know if like anyone would want to see, we have like AQT mod this ideal, and in terms of generators of AQT, like building up for the first few graded pieces, m equals 0, 1, 2, what those graded pieces look like. I don't know if that would be worthwhile to anybody, or would rather see something more dict pathy.
I don't know. All right, I don't know, guys. Any other comments? If not, we can call it quits. We don't have to stay an extra 20 minutes. Thank you for sticking with it. Next week, we'll have Foster, who's going to tell us about LLT polynomials. I'm very excited about that. And then he'll speak for 2 more weeks, and then we'll be done. So thank you for everyone who stuck with it. Sorry this took forever. Hopefully you learned a lot, or at least a little bit. Cool.
Oh, it's been good. Thank you again, Nicole.
Thank you, everyone. All right, I'm gonna probably stop the recording. I should have stopped it a while ago.
And Victor's still talking over there.
Oh man. Stop share. I don't know how to do this. What? There it is.